Hi and welcome back. So in the previous video, we calculated the flux and work done across a simple closed loop in the two-dimensional plane, or rather we sort of discussed the possibility of calculating the flux and work done across a simple closed loop in the two-dimensional plane and how to interpret it. So in this video, let's look at one example of this, and in the process establish a relation between the integral and differential forms of flux and work done. And in order to do that, let's consider a very simple example. Let's say we have the two-dimensional complex plane. So this is the real part of z, or we can call it the x-axis, and this is the imaginary part of z, the y-axis. Let's go to the point z denoted with the coordinates x comma y, z x comma y. So let us focus at a point z in the complex plane, which is denoted by the coordinates x comma y. And around this point, let's draw a simple loop. And in this case, let's consider a square loop of this form, centered at the point z. And for this particular example, we'll imagine that this is an infinitesimal loop, by which we mean that the edges of this square region are, the length of these edges tends to 0, or they are very, very, very tiny. So for instance, the horizontal edge might have a length delta x, where delta x tends to 0. Likewise, the vertical edge might have a length delta y, where delta y tends to 0. And let's calculate the flux carried across this loop if there is a vector field with, say, components u, comma v present in this region of space. Now, you might think that this is once we sort of carry out the calculations, it might seem that, okay, we have taken a very specific example in the sense that we have taken a square, or rather a rectangular loop in the two-dimensional plane, and that brings into question the generality of this result. However, it turns out that even if we consider any loop of any arbitrary shape, as long as it is a simple loop in the two-dimensional plane, the results hold true. And we sort of we can sort of intuitively understand this, which we'll do in a later part of either this video or in a future video. But for now, let's just sort of use the definition of flux and work done that we have been using so far during our review of vector calculus, and just apply it to this infinitesimal loop, and just figure out what is the flux through this loop, and see see some of the interesting results that come out of that calculation. Okay, so this is a sort of rectangular loop or a square loop. We could consider delta x equals delta y as well, but let's just keep it rectangular for now. And we have some vector field denoted by its x coordinate is u and the y coordinate is v, and we just need to calculate the flux across this loop. So we'll traverse this loop in the counterclockwise direction, say in this manner. Now, if you recall the definition of flux, or the infinitesimal flux through a curve or through a segment, the flux is essentially the way we defined it, and I'll put a link to the previous videos, is you take the normal component of the vector field that's present and multiply it with the length of the segment across which you're calculating the flux. So for instance, let's calculate. Let's sort of calculate what is the vector field at this point of the segment. These are our infinitesimal segments. So in the process, when the length of these segments shrink to 0, it really doesn't matter where along this segment we end up calculating our vector field, or evaluating a vector field, and thereby evaluating the flux. So for simplicity, we just take the midpoint of the segment and evaluate the vector field there, and then calculate the infinitesimal flux flowing through this part of the curve. Likewise, we'll calculate the flux through this part of the curve, this part of the curve, this part of the curve, and we'll just add all of those up to calculate the flux through this sort of simple loop in the two-dimensional plane. So let's say the vector field might be pointing something like in this kind of a direction at the middle point of this particular segment, and the components of the vector field will have so the horizontal component of the vector field we are evaluating at a point x plus delta x by 2. So if the length of the segment is delta x, we are stepping half a unit to the right, So we are evaluating this at x plus delta x comma 2, whereas the y coordinate of this point remains the same as this, so comma y. And the v component of the vector field likewise is at x plus delta x by 2 comma y. Okay, so likewise here the u component is being evaluated at x comma y plus delta y by 2, and likewise the v component is being evaluated at x comma y plus delta y by 2, and the vector field might be something like this. So here again we are evaluating this at the u component could be u, x remains the same, whereas y we are stepping half a unit down, y minus delta y by 2, and the v component will be v comma x comma y minus delta y by 2, and the vector field might be somewhere like this. And likewise here we are calculating the vector field might be something like this. So we are evaluating this at u, x shifts half a unit to the left. So I'll just write it here, u x minus delta x by 2 comma y, and v x minus delta x by 2 comma y. Okay. So these are just labeling what the components of the vector field are. I'll just write it on again in case it's gotten a bit clumsy here. So in order to evaluate the flux, we need to take, let's say across this particular segment, we need to take the projection of this vector field along the normal to the curve and multiply it with the length of the segment. Now considering that the vector field itself has a horizontal component which we denote with the symbol u and a vertical component which we denote with the symbol v, the component of the vector field, now the way we have drawn the loop, the horizontal axis of the loop coincides, is parallel to the x-axis, whereas the vertical axis of the loop coincides with the y-axis. So the component of the vector field which is normal to the curve across this segment is nothing but the horizontal component of the vector field. So we take the horizontal component of the vector field. So in order to calculate the flux across the first segment, let's just call it the first segment, we take the horizontal component of the vector field u, which is being evaluated at x plus delta x by 2 comma y, multiply with the length of the segment. So the length of the segment here is delta y times delta y, right? So that's just the flux across this component, this segment of the curve. The v component does not contribute to the flux across this because the v is tangential to the curve, to this particular segment. So the flux of the vector field across this segment is given by this particular expression. Likewise, the flux across this segment will have its normal component will now be the v component, because that's the one that's perpendicular to the segment. So it's v x comma y plus delta y by 2 times the length of the segment, and the length of the segment along the horizontal is delta x. Okay. Likewise, if you calculate the flux across this segment, we'll have the component u, which is x minus delta x by 2 comma y times the length of the segment delta y. Now here there's one interesting thing which we sort of talked about in the previous video, that flux has both a magnitude and a sign. Now once we have decided that we'll traverse this loop in the counterclockwise sense, the rule sort of that we normally apply is that for instance, the normal to this part of the segment will be something that we sort of follow the right hand rule. So if you're traversing the curve in this direction, then the normal is pointing outwards. For instance, here the normal is pointing outwards. If I point my fingers along the direction in which we are propagating along the loop, then the thumb is pointing along the normal to the curve. So if I apply the same rule here, then we are traversing the segment in this direction, so the direction of the normal should be outwards. That will be a positive sense of the normal. However, the way I've drawn the vector here, for instance, the vector is pointing inwards, and so the projection of this vector along the normal to the curve will be negative for this part of the segment. And so here, instead of a plus, I should use a negative sign. Likewise here, the normal to the curve should be pointing here, a positive sense of the normal, whereas the way I've drawn the vector, it's coming inwards. And so the flux, the infinitesimal flux here will be x comma y minus delta y by 2 times delta x. So in this way we have sort of broken down this loop into 4 segments, calculated the infinitesimal flux across each of these segments, and now we sum all of these up to calculate the total flux across this loop. At that point, so we have sort of these 4 terms in our expression, so I'll just get rid of the figure for now. And now we can see that we can combine this term with this term, and likewise this term with this term. Okay, and they both have a delta y on the outside. In addition to that, in the limit that delta x is tending to 0, what we'll do is we'll take, for instance, this term ux plus delta x by 2 comma y, and do a Taylor series expansion. And we'll do a Taylor series expansion of this term. So let's just focus on these 2 terms to begin with. If I do a Taylor series expansion centered around x and just retain a couple of terms in this expansion, we'll have u, and just in case we, as a reminder of Taylor series and what Taylor series expansion, we haven't covered these in detail, but a part of this we touched upon when we were talking about perturbation theory. So I'll try and find, try and put a link to that particular video, but in future hopefully we'll sort of discuss Taylor series expansions and all in more detail. So if you look at this term, we can expand this in the form ux plus delta x divided by 2 times du dx, the partial derivative of u with respect to x. And let's just retain the first order term. So we just have 2 terms here, ux and del x by 2 du dx. And likewise we expand this term. So we'll have minus ux, or rather minus ux minus delta x by 2 du dx, and this whole expression is multiplied with delta y. So this is just considering these 2 terms to begin with. Let me just call this df1, which is coming from a combination of these 2 terms. Now if we open these brackets, we'll have ux plus delta x by 2 du dx minus ux plus delta x by 2 du dx, and this whole expression multiplied by delta y. So we see that this cancels out, and what we are left with is these two get added up. So we have the partial derivative of u with respect to x times delta x delta y. Likewise, if we sort of take these 2 terms, do a Taylor series expansion of v, what we'll find is the second part of the flux, which is dv dy delta x delta y. Okay. So the reason why this has a dv dy whereas this has a du dx is because when we look at these terms, we are sort of expanding in powers of y. So we have a term of the form vx comma y plus delta y by 2, which we sort of do a Taylor series expansion and approximate as vx plus delta y divided by 2 dv dy. And so in the same way that we got a du dx for the first part of the flux, we'll get a dv dy for the second part of the flux. And then when we combine these 2 terms, we'll find that the total flux is of the form du dx plus dv dy. These are common factors which are common to both of them, times delta x times delta y. Okay. Now this expression is the infinitesimal flux through a loop, through a simple square rectangular loop with dimensions delta x delta y. of a vector field with components u comma y in the two-dimensional plane. Now notice that delta x times delta y is nothing but the area of the loop. So this can be thought of as the infinitesimal. So I'll just use the delta and the d interchangeably for now, in the sense that we'll be sort of taking all these expressions in the limit that delta x goes to 0 and delta y goes to 0. So let me just write down delta x times delta y as the infinitesimal area of this loop and just denote that by dA, the infinitesimal area. Whereas if you look at this expression, this is nothing but the dot product of this operator, the gradient operator, with the vector field which has components u comma v. So if you have a vector field, say E, with components u comma v, then this is nothing but the dot product of the gradient operator with E. And this dot product essentially involves the gradient operator has x component, which is denoted by, in two dimensions, it has an x component which is denoted by the partial derivative operator along the x direction, comma the partial derivative with respect to y along the y direction, dotted with the vector field u comma v. And this dot product is carried out in the same way as ordinary dot products or inner products, where we evaluate du dx. So this dot product essentially means the dot, you sort of differentiate u with respect to x as the first component of the dot product and differentiate v with respect to y as the second component of the dot product. And if we carry out this calculation, we'll see that this gives you nothing but du dx plus dv dy. Just like the dot product of any two vectors. So if you have two vectors with components, let's say a comma b, and you dot it with another vector with components x comma y, we'll end up getting a dot x ax plus b dot y dy. And it's exactly the same operation that we sort of do here, except that we are differentiating the vector instead of just calculating a normal dot product. So when we evaluate the infinitesimal flux through this loop, we find that it's composed of two components. One, which is the dot, or which is del dot the vector field, some vector field E, which has components u comma v, times the area, infinitesimal area of the loop. And if you've done some vector calculus before, then this component del dot E is called the divergence of a vector field. And hence sort of the title of this particular video. So this is an interesting result, because what this tells us is that the infinitesimal flux through a small loop in the two-dimensional plane, for instance, is nothing but the divergence of the vector fields times the area of the loop. Or to flip the definition around, we can define the divergence as the infinitesimal flux divided by area. Okay, and here the E by E, I just mean a vector field with components u comma v. Okay, so that's one of the results of this particular video. Now, if we carry out exactly the same calculation like the way like the one we did for the flux, if we carry out exactly the same calculation with the vector fields, for instance, depicted in this manner with components u and v, and calculate the work done along this loop, the infinitesimal work done, where instead of taking the normal component, we take the component which is tangential to the segment and sum up all the work done, the infinitesimal work done across all the four segments. We'll find that this gives us an expression which looks like the curl of a vector field times the infinitesimal area, or rather the cross product of the gradient operator with the vector field times the infinitesimal area, and this cross product is called the curl of the vector field, which is the other part of the title of this video. Or in other words, we can sort of again flip this definition around and say that the curl of a vector field is nothing but the infinitesimal work done divided by the area of the region of space that we're considering. So it'd be good sort of just to carry out this computation at your end and see if it indeed matches up this expression. And again, just like the dot product definition is an extension of what we know from ordinary vectors, where we just take the dot product of two vectors, the curl or the cross product is defined in exactly the same manner, where we have a vector field where we just consider a field with components d dx, comma d dy, and take its cross product with a vector field u, comma v. So hopefully you'll sort of see this result emerging. If not, we'll take up this example in the next part of the video, and we'll focus on this example, just work this out again, and sort of carry forward the discussion in how sort of these things all glue together and help us understand complex integrals. So hope this was a quick reminder of some of the ideas from vector calculus, and hope to see you soon with many more interesting results. So thanks for watching.